right. Hello, everyone. My name is Adam. I'm a robotics programmer. I've got a few years under my belt of doing this, and one trend I've noticed, I get a lot of questions about people asking the most efficient way to handle pallets, arrays, trays, whatever you want to call it. You have dozens or hundreds of parts in a nice array, and you want to avoid having to teach the robot every single part. Um, for example, a machine tending operation. So I just want to show you, the way I've done it, the way I've been successful. It's not the end all. Everybody likes to do things their own way, but I'm going to show you how I do it. In the meantime, I do just want to say that if you've not taken FANUC training, jump onto their website, fanucamerica.com, take a basic handling tool class. It'll really pay off. Everything I'm going through right now is going to be based upon the assumption that you already have some core programming knowledge. You understand how to teach points. You understand what offsets are. You understand some basic math and spatial reasoning. If you don't, no problem. FANUC will get you trained. This video is not sponsored or paid for by FANUC. I'm just doing it because I get this question all the time. It'd be easier just to point people to this video. So let me show you what I've built, get you kind of up to speed. First of all, this is RoboGuide, the offline programming suite. Great tool for quick programming. I've put in the FANUC M10ID12 model. It's a great 1.5-meter reach robot, real good for machine tending. I went ahead and just built this dummy little pallet, built a little chuck workpiece holder. This is all representative stuff, just to give us something to play with. Yes, the door is shut. We're going to be reaching through a shut door. Nothing fancy. This is just for learning. So the first thing I want to point out, a great place to start. So if you're new, you're beginning, a great place to start under data and position registers. I'm a position register guy, a PR guy, not a local points guy. It's because PRs can be used in a multitude of ways across a multitude of programs. They can be changed on the fly. Just easier to use. You're going to notice that I can run an entire pallet of parts and interface with a machine. I can do everything with only 3 points and 2 offsets. Okay, so this is the point of modular code. The robot's going to have a home position, which I've taught is this, just a nice safe spot away from everything. It's going to have a tray pickup position. So I named it tray, but really what it is, let me go ahead and pop this open. I can tell the robot to move. This is a benefit of RoboGuide. Robot, move to the first part. Boom. This PR2 is this point. It is the very first part. So I could have called it part 1. I didn't want to call it part 1 because it's going to be used for all my parts, but it's the origin of the tray. I also can go here, tell the robot, move to, and boop, robot goes right there. It's in the machine, nice and lined up, right into the chuck. That's the position that I named as chuck. All right, so I've taught what is going to be my origin part. I've taught where the parts will be going into the machine, and I've taught a home position. That's it, 3 points, okay? This offset, I'm calling it Tool Z100, TZ100. If we look at the data in there, nothing X, nothing Y, 100 Z, and 0 yaw pitch roll. Excuse me. This is because with offset math, I'm going to apply a Z offset of 100 millimeters to my pick and place position. That way I don't need to teach points above the part. I can tell the robot to move to a point 100 millimeters above where you need to be. You'll see that in the code. Then I'm also building what I call a tray offset array of in PR6. I'm going to put this at 0 for right now. Right now I'm starting it all at zeros. There's no data in there, okay? But that tray offset is going to become the offset data for these parts. So I'm going to start with my very first part that I taught as tray. And I know that in the X direction, I don't know if you can see it in this triad, my X direction has a 50 millimeter pitch. My Y direction has a 70 millimeter pitch. And I've got a 3x4 array that I want to cover. I'm going to do that all with math and only one taught point. So how are we going to do this? You'll also notice in my registers, numerical registers, I've named one as my X index and one as my Y index. We can actually go ahead and zero these out to begin with if you want. Doesn't matter. We just need to know that there's a numerical register for however many parts are in the X and a numerical register for however many parts are in the Y. All right, so we're just building. So far all we've done is commented that code and taught 3 positions, okay? So I haven't actually done anything yet. Most people like to have a homing routine. Homing routine is normally, open the grippers, go up to a safe place, retract home. It's normally a good piece of code. Since I'm in RoboGuide and I can't break anything, my homing logic is just to move joint and go home. So, if I run this, you'll watch the robot like crash through the machine. Just to give you an example here. So, run. Whoop. But in real life, your homing logic might be something else, okay? What else have I written? I've written some of these programs called pickup chuck, pickup tray, place chuck, and place tray. What these are not relevant to what you need to do. These are in RoboGuide only. It is to tell my virtual robot how to pick and place virtual parts. For you, you'll just be opening and closing grippers, which is either robot output RO or digital output DO, depending how your valves are set up. So you don't need to worry about those. Let's go ahead and just jump into my main routine, and I'm just going to walk you through how I like to program these, all right? Real short, the whole thing's only 34 lines, and that's with gaps and comments. It's really probably only 10 or 12 lines of code to run this whole thing. First thing any good programmer should be doing is you should be setting your frames. This one I'm not using. I never set up a frame for the tray. This is RoboGuide and I don't care, so I'm programming in World. I did, however, set up a tool frame for this tool so the robot knows how to carry things. I set my payload. That's always important for speed studies. Changes your ax and dex. Override. This is how fast the robot's going to run when I hit go. Sometimes it's wise to start your program nice and slow, and then later you can bump that up and really get making production. For here and now, let's just start it slow so we can watch it, maybe even a little slower than that. Okay, next line. What am I going to do? I'm going to make sure the system's at home. You've already seen that in my home routine, it just tells the robot to go home. That's not near enough for regular production, but it's what I'm doing. All right, here's the magic for starting to learn how to do these in loops. In order to run these parts in loops, we're going to be using a data set that manipulates, let me jump back here, that manipulates the values in the X and Y of tray offset, which means the first thing I want to do is I want to initialize my data. Here we go. 2 lines of code. When you look, let me go ahead and show you where this is found. Instructions, registers, and then option 8. And then over here, you're going to see one called PRIJ. It's going to show up all blank like that. PRIJ. The I is the index. Okay, it's what position, what register, right? So these lines above, I'm saying, okay, I want PR6, which is my tray offset. The J is what element. So all PRs have 6 elements. At least for this tutorial, we're going to stick with 6. To where you have X, Y, Z, yaw, pitch, roll. They are that in order: 1, 2, 3, 4, 5, 6, X, Y, Z, yaw, pitch, roll. So if I want to play with the Z value, I would put in a 3. You know, if I wanted to, you know, change the roll or something, I could put in a 6. Okay, it's just whatever you want to mess with in there. I'm going to delete this. We don't need that. Just showing you how to get there. But in my initialize, I'm saying, okay, the offset data of PR6 element X starts at 0. The offset data of element Y starts at 0. So this is just putting everything at 0, 0. So if you look at this, I'm considering this bottom right guy as my 0, 0, and my positive X will be counting up, and my positive Y will be counting out. You can do that however you want. I'm used to doing that just because of how the robot is set up. X, Y, the right hand rule. You can do it however you want. Okay, so let's go back and let's look at back in our main program. Okay, so we've made it down to the initialize data. Now I want to set up some for loops, FOR, for loops. You can do it in either direction. You can do the Y direction first or the X direction first. Does not matter at all. But what does matter is whichever direction you want to do first will become the inner loop. So the way I have it written is we're starting in the 0, 0. We're going to start. What's going to happen is the Y index will start at part 1. The X index is going to do 1, 2, 3. So it's going to go boom, boom, boom. Then once the X has done all 3, it's going to reset. Okay, and when it resets, the Y will go to number 2, which is here. And then X will go 1, 2, 3. And then it'll reset. And then Y will go to 3. And then X 1, 2, 3. And then Y will go to 4, 1, 2, 3. So visually, what that looks like is what you're seeing on the right side of your screen. X will go 3, then reset, index Y. X will go 3, reset, index Y. X will do 3, reset, index Y. Okay? So set up your for, which if you need to see how that's done, it's just instructions, next page, and it's option number 7 down here. 4. While we're talking about the for loops, I'm going to scroll down and show you that there is an end for and another end for. All right, and then the program's over. So anywhere you have a beginning of a for loop, you need an end for. So let's look first, try and get this all on the screen at once. Here's the X looping. For X 1 to 3, and it just bumped me out again, but you can see here. There we go. For X 1 to 3, and then end for. So this is a loop. If you kind of see my mouse, it's just going to do this 3 times. 1, 2, 3, and then index, and then 1, 2, 3, then index, and 1, 2, 3. So what are we doing? First thing we're going to do is I'm going to call a program that says tray to machine. That sounds exactly like what you think you're going to see in there. It's a very, very simple program where the robot is going to move linearly to PR2. Remember that tray position I taught? It's going to go there quickly. My favorite line for continuous is CNT 25, nice smooth motion. And here's your magic. This is the magic right here. These 2 lines, okay? The tool offset that we added, that TZ 100 millimeters, it's going to add 100 millimeters to the start position in the Z. So that should put my robot, we can actually do this, step mode, shift, forward, go. Okay, so the robot is currently 100 millimeters above my first part, okay? I also have the offset of the tray offset, which if you remember is all zeros right now. There's nothing in it. So it's poised, it's getting ready to go pick that first part because there's no other math in there, okay? Move forward. Now it goes down to the part. So the difference between line 2 and line 3, if you look, they're the exact same line. The only difference is line 3 does not have the tool offset. So I'm just going linear to PR2 with a Z offset and a null tray offset. Then line 3, I'm going to the tray again, same point, but just without there's no Z offset, okay? I'm going to go ahead and function abort and get out of this. Then this right here is I'm calling a simulation program. I'm telling the robot to pick up a part from the tray. What yours will look like in real life will probably be something instructions, IO, robot output, you know, maybe number 1 turns on, whatever. You're going to turn on a solenoid, you're going to turn on a valve, you're going to give it a little debounce so it can actuate. And then line 7 looks identical to line 2. You take a look at that. It's identical because all I'm doing is I'm above the part, then I'm down to the part, I'm gripping the part, and then I'm above the part again, 100 millimeters. Okay, so if I do that step forward, now it's back up. Okay, let me function abort out of here. Okay, I also don't need this for my simulation, so I'm going to get rid of it. To show you real quick what it looks like to teach a point and then add all those, let me go ahead and show you how to do that. It is point, linear, continuous. I don't want a p-value, so I hit choice. It's a PR. I want it to be PR2, my top position. I want to put a speed in there. I want my CNT to be 25, maybe 50 if I'm feeling crazy. And then right here, see how this is highlighting nothing? Choice, tool offset is number 6. My tool offset I had programmed as PR5. Now you see how it's highlighting nothing again? Choice, offset PR. Now this is a frame offset. There's a tool offset and a frame offset. So anything I put in here is going to be relative to world or relative to the user frame that I programmed. 6. See that? So there you go. That's how I built that line. So I'll go ahead and delete that. Yes. So that'll pick up a part from the tray, and then no surprise, I want to go in the machine. It's going to look the exact same, except the only difference is I don't need all the offset math. So I still need a tool offset so that I can go above the chuck and then down into the chuck, but I don't need the PR6 stuff. So linear to P3 above it, then linear to P3 fine. Fine means I'm stopping there, right? Drop it, debounce, and then linear to PR3 above it again. So it's above it, into it, let go, above it. Real easy. And then go back home. There you go. I don't know why I have a ton of blank lines. Probably just, I like to add in a bunch of lines when I'm debugging things, so we'll just delete those. It doesn't hurt to have blank lines, by the way, just if you're OCD. Another nice thing that I like to do is if I know I'm going to be reusing this all the time, edit command, copy, select, and you can scroll and highlight all of this and say copy, and then like if I want to go down here to the end of my code, paste, logic. Now you can see that I just added all of the code again. So it's really easy to copy and paste code. So once you write it once, just copy and paste it use it everywhere. There, I'm going to delete it. But really nice. So that's it. I'm going to pick up from the tray and put into the machine. Let's go back to my main routine. That was me discussing to you picking up from the tray and putting to the machine. Well, now the machine has to do something to the part, right? So the robot gets out, waits. Now we got to go machine to tray. So it's the exact same code, just in reverse. I go pick from the machine. So I'm going to go to the chuck, above it, to it, grab the part, get above it, go home, then go above the tray, down to the tray, drop it, above the tray, go home. Okay, so really easy stuff inside the loop, okay? So inside this loop that we're going to do over and over and over and over, it's get a part into the machine and get a part out of the machine. Now what do? Everything was at 0, 0, okay? We need to index that. So after I do this first part and I pick it and I place it and it gets machined, and then I take it out of the machine and I put it back, I just want to do everything I did again. I just want to do it there. So what do? Get out that PRIJ instruction. PR6, which is our tray offset, element 1, which is the X. I'm going to say PR61 equals its self plus the pitch, which for me is 50 in the X, it's 70 in the Y. So I said, okay, 50 millimeters in the X. So now what I'm saying is my X offset, it used to be 0. Now it's 0 equals 0 plus 50. So now it's 0 plus 50 is 50. So now the next time the robot runs, it'll want to do all its work there. So it'll go 0 to 50 to 100. And that's the end of the 4, right? So 0, 50, 100, done. Well, now it has to index, it has to go to the Y, okay, which means I have to reset my X. My X went from 0 to 50 to 100. Okay, I need X at 0 again, and I need Y at 70, because that's my pitch over here is 70. So what do? Outside of the for loop, I reset the X row data, 6, 1 goes to 0, boom, so 0, 50, 100, boom, back to 0, and Y offset. Whatever the Y used to be, I want it to be Y plus 70. So 0 plus 70 is 70. So the Y will go 0, 70, 140, 210. And then that's the end of that loop. And then the rest is just good. That's it. The loops will take care of themselves. It'll run. Should be great. Let's watch this thing run. You can kind of watch the code execute on the left while the robot runs on the right. Let me hit play. So we should go home. There we go. All right, so we pick part 1, load, unload, put it back. Part 2, load, let it machine, unload, put it back. Part 3. I'll go ahead and turn this view. There you go. So now you see how it indexed over. Now it's going to get that one. So now this robot is just running these 4 loops, 3 in the X and 4 in the Y, which, hey, your rows and columns will be whatever you need it to be. And it's just going to run. Now let's simulate that somebody e-stops or they break a fence circuit, right? You got a fence around the robot, someone comes walking in, all right? It doesn't really matter, robot gets apart, wham, they break in, all right? You're gonna see that the program is retentive, so it's paused. The program knows that it's on line 11 of tray to machine. It knows where it is. You'll see the status says paused. So somebody gets in, they do whatever they weren't supposed to be doing. They walk out, they shut the door. As soon as they shut the door and you hit the green button again, robot takes right back off like nothing happened and just keeps running production. All right, it's just good to go. That's a benefit of just FANUC retentive programming. So we'll let this thing finish, get through all its parts, and when it's done with its parts, that's it. There we go. So it did the X loop 3 times the Y loop 4 times, did all 12 parts. It's done. At this point, what you want to do in your code is you want to have some kind of light or audible or signal or something to a PLC or a PC, whatever you want. You can even have the robot send you an email, doesn't matter. But let the robot let you know that the tray is done. Somebody comes in, they remove the tray, they put a new tray of blanks in, and what's great is, if you remember, the robot will automatically initialize when you start the program from the top. So it was doing all this math. You don't have to do anything. Put the new tray down, satisfy your safety, hit go, and the robot will know. Start back over at number 1. Get to work. Get it done. So that's it. That's my favorite way of doing loops. Let me one more time show you on that main screen. I'll even do a little split screen so maybe you can see more at once. Set up your frame. If you've set that up, it'd be your tray. Set up your tray frame, your tool frame, your payload, your speed. Have something that gets the robot to a safe position. Have something that puts everything at 0, 0. Set up your inner and outer loops. Set up your actual motion in and out, into the machine and out from the machine. Here's the entirety of the X loop 1 to 3. It's just into the machine, out of the machine, index, repeat. Into the machine, out of the machine, index, repeat. In, out, index, repeat. And after that third one, what does it do? It goes down to line 27, resets the data, indexes the Y, and then brings itself automatically back up to here, and then does it again. So it's 1, 2, 3, out, up, 1, 2, 3, out, up. So it's doing the 3 times, 4 times. Hopefully that all makes sense. And remember, the only points you really needed to teach was home, tray, chuck, and an approach and retreat distance, and a PR that holds all of the what becomes your math. So hopefully that helps. Always feel free to contact your local FANUC rep if you have any questions, and thanks for watching. Happy coding.